Good evening, everyone. Welcome back to NPTEL live session for the course Circular Dichroism and Moss bar spectroscopy for chemists. So this is the fourth week. We are going to discuss about the assignment problems and the basic concepts that have been covered in fourth week lectures. That would be mostly comprising of the chirality and enantiomers, enantiomeric axis, etc. So we will wait for a few minutes for others to join and then we will start. So just to give you a brief what we have covered so far in the last three live sessions. So firstly, we saw the symmetry we have talked about, which comprises of its symmetry elements, symmetry operations. Corresponding to that, we have also seen the point group, the order of your compound, and we have also seen how to find out a point group. Then secondly, we related symmetry with chirality, and we found that chirality exists when there is no improper axis of rotation is present, that is Sn, or to more precisely saying it, Cn or Dn should be the point groups. Whereas we saw that even if H2O2, that open book form, is having C2, that means it belongs to Cn point group, still it is not chiral because of single bond rotation. So rotation is that fast that it will it is having the mirror image, which is superimposing the mirror image itself. So therefore, even if it is having a CN point group, it is not being called as a chiral. And then we saw yesterday's live session, we saw various amino acids, around 20 number, which are comprising of the aliphatic part, say for example, alanine, glycine, etc., where it is having CH3 as R group, it is having H as R group. Second, we have aromatic one, say for example, phenylalanine, which is CH2. Then we were having basic, which is comprising of more NH2 units. We were having acidic amino acids, which are having more than one carboxylic acid group. Polar amino acids, for example, this serine, which is having CH2OH, and sulfur or selenium containing amino acids resolve. And also a secondary amino acid we saw, which is proline. So these were the basically amino acids which are chiral in nature, and we found, and mostly are in L form. And we found that how to assign L or D to any amino acid, we need to follow the rule called CON, where CON stands for carboxylic group. This is any R substituent, and nitrogen is your amine group. So if your R group, your H is at the back side, NH2 facing above the plane, and COH is here, give the numbers going from CON 2 and 3. If going from 1, 2, and 3 is going to left side, this is your L form, that is an anti-clock. Whereas if we have carbon R, COH, NH2, H, this is 1, this is 2, this is 3. Now 1, 2, 3 is going clockwise, which is right. Therefore, it is given as D amino acid. So this way we can assign the L and D isomers to the particular amino acid. So till this point of time, we have covered these many topics. Now the next point is talking about the chirality, how it requires, what kind of environment it requires to recognize a molecule. And also we talked about the lock and key mechanism. So these are the assignment problems for this particular live session. We will be taking up each and every question at the end of the lecture once the concepts have been revised. So the topics that will be covered during this lecture are the follows, are written as here. Chirality and the chiral environment. So firstly, we will take up this part. So we already understood, right, what is chirality, right? So now, firstly, we will talk about the chirality and its chiral environment. So chirality, we already know that it is a key tool for the biology. How? Because it helps in molecule recognition. which can be explained as, so if we have this log or any substrate for that matter, and you have these three shapes, only this is going to fit here, which is called as key. So like one key for particular one log, that is where this kind of system, which is having certain chirality, it will fit it there. So it will recognize your molecule. But where and how we can get it? So how do we detect our chirality? It can be detected only in chiral environment. So if an environment is chiral, then we can detect this. For example, now the second point will come as enantiomeric axis. See, you have enantiomers A and B. So if A content is equals to B in terms of composition, so this creates a achiral environment. Zero enantiomeric axis. So none of this is more than 50%. Therefore, it's zero enantiomeric axis, where enantiomeric axis is nothing but your total amount of enantiomers upon the axis of this. Whereas if I have if A is greater than 50%, say 60% than B, then this is having an enantiomeric axis because one enantiomer is present in axis, and this will create your chiral environment. So this would be suitable for detecting of the molecule, for recognition of the molecule. So in case if both the isomers are equally present, that is not going to help in any condition. We need to have one enantiomer in axis. So now how nature is helping, nature helped to have this chiral environment. So it has been said that Murchison meteorite was the first to strike this earth, and it was comprising of many amino acids, which are chirals. So that created a chiral environment to make or to recognize carbohydrates, proteins, etc. So the composition of this one was having serine, glycine, alanine, glutamic acid, leucine, valine. So they were in axis, so they created a chiral environment. Besides this, there were other amino acids present. Say, for example, derivatives of serine. So we have NH2. I will not draw all of them. You can go back and watch the videos. So here, if you can see, this is the chiral center, and this is called as isoserine, where serine we already know that it was CH2OH group. So here it is additional CH2. it's a secondary, or second we can take an example like CH3, NH2. So we have two chiral centers over here. This is called isothreonine. So we have already read these names in the last live session. So you can go back and etc. There are many others. So therefore, we talked about the chirality and the chiral environment in enantiomeric axis and Murchison meteorite. Also, if now we will talk about the light and matter interaction. How light interacts with the matter. So we know that normally all the ground state, all the electrons will be staying in the ground state. The population will be high in the ground state until unless any light affects it. So if I am giving the light source to the electron over here, it prefers to go to the state, which is an excited state. And this is your energy profile diagram. So how this light is interacting with electrons. So for that, we need to understand the Schrodinger wave equation, which is nothing but H psi equals to E psi. So H psi equals to E psi, where H is your Hamiltonian, psi is your wave function, and in E is energy of the electron. What happens when light or photon strikes the electron? It actually disturbs or perturbs the electron density distribution. Because of this, Hamiltonian changes, and corresponding to that, energy changes. That's why it goes from its ground state to the excited state. So if it is in ground state, the Hamiltonian will be written as H ground E, and excited state is H. The wave function changes. Excited state will give you E star psi excited state or E star. So when we have this kind of system, actually the light radiation that we are using, why it is interacting with our matter, it is actually comprises of two kind of wave. One is magnetic field and another is electric field, and they both are perpendicular to each other this way. It is E vector, it is B vector, where both are perpendicular to each other. So E content is more than the magnetic field, so its amplitude is high. Therefore, it actually affects the perturbation, or it creates the perturbation. So once it interacts, so when there is a strength of electric field, say for example, this is my compound, and now the electric field is coming like this way, resultant would be having some perturbation. So perturbation in the electron density happen. So therefore, we see the transition from the ground state to excited state. Just a second. Okay. So now if we'll see that on what factors this interaction is going to depend on. So it depends upon the strength of the electric field and the polarizability factor. So to what extent strength of the electric field and polarizability, which is defined as alpha. And how do we know? So you saw that light radiation is having electric field and magnetic field. So this is in more amplitude. It perturbs the electronic density distribution, which changes the Hamiltonian and which changes the energy. Therefore, transition from ground state to excited state happens. So this is a flowchart. Now, how do we know that certain electronic transition is possible? So for that matter, we have a transient dipole moment, which gives you the probability of electron density distribution from ground state to the excited state. And the formula is going from minus infinity to plus infinity, wave function of excited state, dipole moment vector, ground state into d tau. This is a volume element. So when this transient dipole moment minus infinity to infinity, excited state, vector, ground state, d tau. There for different, it could be dx, dy, dz for the volume element or corresponding to each direction. So this dipole moment vector is nothing but into alpha. This is your polarizability, the extent of electronic perturbation. So if this value is 1, then the transition is allowed. If this value is 0, then it is forbidden. So I hope you guys have understood. Now, up to this point, why we are talking about the light and matter interaction, we will get to know about it because we were talking about the molecule recognition, which requires the chirality or chiral environment. And for that, we need to understand how the light interacts with matter, because light itself could be a source of chirality. And here we got to know that electric field actually interacts with the matter polarizability, and we got the transient dipole moment factor for a transition to be allowed or forbidden. Now the next question is how much interaction will occur. Say for example, I have this solution containing my compound. Now I'm giving the light. It is comprising of electric field. So how much it is going to take up? The interaction is going to how much? So for that matter, a new terminology will come that is called the absorbance. How much it has a capacity to absorb the light. Say for example, here we have a solution, and here the intensity of the light was I0 and it emitted out I. So your absorbance would be log of I0 by I. Now, what are the factors on which absorbance depends? So first thing, if we have this solution, and if we have this solution, this is highly concentrated, this is diluted. So when we have highly concentrated, there's more chances of absorbance. So therefore, absorbance is directly proportional to your concentration, which is in molar. Second, if the concentration is constant, and path length is different, then, say for example, here the concentration is same, but here it is having more path to go. So therefore, more absorbance. So absorbance is directly proportional to your path length. And third is molar absorbance coefficient, which is epsilon. So this is actually property of the molecule. So depending upon the molecule's property, E value would be different, and A is directly proportional to epsilon. Therefore, since we saw it is directly proportional to L, so it becomes epsilon equal. This is your absorbance formula. It is not having any units, because Absorptivity is having molar. Centimeter inverse. This is molar. This is centimeter. So everything will be cancelled out. Absorbance would be A. Now the next thing is, we know the concentration path length factor. Now how do we know what is E and how it is different for rest of the things? So this is how much this is a factor that how much electric field is interacting with electron density redistribution. So since we know that electric field actually oscillates, so it goes like this is crest, this is trough, and when we have a substance, it will go like this way, making the electron density. So E actually depends upon the oscillating function, which is 4.315 into 10 to the power minus 9, mu1 to mu2, what would the epsilon d nu. So from going from 1 to 2, mu1 to 2, say for example here. So epsilon and mu, that is wave number. If we have this kind of plot and the other is, so at mu1 value and mu2, this is my area under the curve, and this one, the whole one is this. So it is having more value, more distribution compared to the other graph. Now, there are some transitions, generally transitions that happen is d orbital transition, n to pi star transition, pi to pi star transition, and the trend is pi to pi star is having very low gap. So these are like very small in length, energy difference is very small. So therefore it will be having longer wavelength and epsilon would be very high. So pi to pi star transitions would be highly allowed because of the same orbitals also. Then n to pi star transition, it's around 1,000, 5,000 to 10,000 range. This is also allowed, but D to D transitions, they are very low epsilon value. So till now we saw that how the light and matter interacts. What is the transition moment integral? How do we know that what amount interaction can happen? So oscillating function, absorbance value, everything we saw. Now the second question is why we actually were interested in the light. We started with the chiral environment. Why we are talking about the light? So we need to say that whether this light is chiral or not. Say for example, the white light that we are taking, it would be going in every direction. So when we have a polarizer over here, so this is a polarizer which will absorb all the radiations in all the direction except one. So it will give you only one which is not being absorbed by it in one particular side. So this is called a polarized light. So if you will see that whether my polarized light is chiral or not. So if you will see that we are generally drawing it like this way. So it starts, suppose, from this part and then going to the way it moves. Sinusoidal you all have seen. So right now it is here, then it goes here, then it goes here. So this is the way we are drawing it. Then it goes back. Now it is coming down and here it would be maximum. So if we inculcate it, it would become a like this arrow. And if I am making it, if it goes like this form and its mirror image, so this is right circularly polarized line and this is left. So if you'll see, these two are mirror images but non-superimposable. So when we have non-superimposable mirror images, that creates chirality. Therefore, our polarized light is chiral in nature. Now, we saw that if this RCP is not equal to LCP, that means it moves with different speed. Then something generates called optical rotation. For example, we have so RCP is this side and left hand is only this much. So the magnitude of your RCP is more than LCP. So the resultant would be towards right side. So this optical rotation happens to the right side. This optical rotation is actually given as phi, which is dependent on NL minus NR, or the formula is 180 degree into L. That is pattern NL minus NR upon lambda, where NL is the refractive index of LCP and NR is the refractive index of RCP. This is the formula that we are looking into. So with this much, we can identify and we can quantify the degree of rotation when our molecule is in the plane polarized light, because plane polarized light is chiral, and therefore we can detect our molecule recognition can happen based on the rotation that happens to right side or the left side whenever it is placed in plane polarized light. So this was the basics that has been covered in the lecture, the 4 lectures. So we have covered these all points. Now we will take up the questions. So the first question is, chirality is a key tool for biology because, so it's a very straightforward question. We have already talked about it many times that chirality is a tool which helps in the molecule recognition. So looking at the options, it helps in molecule synthesis, with molecule recognition, disintegration of the molecule. So the B option is correct. Now for a transition to be allowed, the value of transient dipole moment should be. So we already know that transient dipole moment, we defined it as going from minus infinity to plus infinity. The wave function for the excited states, then dipole moment vector, ground state into d tau, which is a volume element. If it is 1, then it is allowed. If it is 0, that is forbidden. So only 2 cases are there. So this option is not possible. This is not possible. And since it is called as allowed, so our option is C. Now, the absorbance of the substance also we have seen. Absorbance of it is given as E, C, and L. So it is dependent on the concentration. It is dependent upon the path length. It is dependent upon the molar absorbance. So all of the above or none of the above. So option D is correct. This is a very straightforward question. Now we need to write the decreasing order of the molar absorbance coefficient value for these transitions, as we already saw that pi to pi star transitions are having more epsilon value than n to pi star, and d to d transitions are having the minimum. Which of the following statements are true about a plane polarized light? It is a monochromatic source of light. That means having a single frequency. So it is true. It is chiral. It is achiral. No, none of the above. So option A and B. Now, 6th question is, if the light left circularly polarized light moves faster compared to the right circularly polarized light, if LCP is greater than RCP, then optical rotation will happen in which direction? So we will take up this question. So here it is saying we have this general case is this one. And now we are having this thing. We'll just make a cross section. So it is saying that LCP is more, say for example here, and RCP is just a bit like here. So if you see the magnitude, it would be like in left direction. So optical rotation will happen towards the left side. So the correct option is B. Now, the 7th question is given as, since we know that optical rotation phi is equals to 180 into L, and L minus NR upon lambda. It is given L equals to 1 decimeter, 400 nanometer, and NL equals to NR. Since this is N equals to NR, this becomes 0. Once this is 0, therefore there is no optical rotation, which says that LCP and RCP is equal. There is no change into that. So therefore there would be no optical rotation. It will remain as such. So answer would be phi is equals to 0. So this is what we had, what we understood in the lecture, what we started with, that so we started with explaining the symmetry elements, operations, symmetry's relation with chirality. Then we described different amino acids also in the last lecture. After that, talking about how to assign L and D form using the Kohn rule. Then these are the assignment problems that we discussed. But before that, we saw different topics that have been covered in the live session, the week lectures, chirality and chiral environment. We saw that it's a key tool for the biology to recognize the molecule, and it goes to the lock and key mechanism. Then we had enantiomeric axis. One of the enantiomers have to be in more quantity compared to the other, so that we can have an enantiomeric axis that will give you a chiral environment. So we talked about how this chirality comes in amino acids or something, because that occurs naturally when meteoroid strikes the earth, and there were a composition of many amino acids, and from that only we got carbohydrates and proteins and life started. Then since we were talking about the chirality, so how do we make our molecule chiral when it comes under the light? Because light itself is giving a chiral environment. Then we saw the relation of light and matter interaction. To have a transition from ground state to excited state, there should be some criteria for which we can say that this transition is allowed and this that is not. That is being judged by the transient dipole moment, the formula that we gave, and where we said that so this factor, when it is more equals to 1, that is allowed transition. If it is less than 1, that is forbidden. So after that, we saw the how we know that light is interacting with the matter and how much it will interact, that will be judged by the absorbance value. So for example, you're giving not amount of light, but it is giving out I amount. So absorbance would happen as a ratio, logarithm of the ratio of I naught by I. And on what factors absorbance depend. To have a maximum absorbance, we need to have a concentrated solution. Then the path length, the travel timing or the path of that light should be more. And also the molecular property, that this molecule is having the property to allow that absorbance to happen. So that is equals to A equals to E epsilon CL, where absorbance is not having any units. So now what is E? E is actually that factor which defines that how much electric field is going to interact with the electron density distribution. Since the electric field is having an oscillation, so we mainly talk about the oscillating field. And when the oscillating field strikes on the electron density, it actually perturbs. And that factor is coming from this oscillating function. So more the area under the curve between epsilon and wave number, that would be having more distribution. Therefore, there would be more absorbance. Then we saw that these are different kind of transitions that can be seen in a molecule, and depending upon like which one are allowed, then they would be having more epsilon value. After that, we saw that when we are talking about light and matter interaction, we understood it, but why are we even focusing on the light? Because this is chiral or not, that we will check. Since white light, if you will take, that will have a direction that will orient or oscillate in every direction. So we need to use a polarizer that will restrict only one particular light and let it to pass through. Otherwise, rest of this would be absorbed. And here we get a polarized light, which is called as a monochromatic light, having only one wave number of frequency. And once this is there, now we understand that it would be a sinusoidal curve. It would go like this particular way. And when we draw a mirror image of it, both the mirror images, right, LCP and RCP, right circularly polarized light or left circularly polarized light, they are mirror images, but they are non-superimposable. Therefore, when we have non-superimposable mirror images, that creates the chirality, and thus we got to know that chiral light is polarized light is chiral in nature. And when we are putting our object into the polarized light, it will either uh, rotate the light in a right direction or in the left direction, depending on which one moves faster, either RCP or LCP. And this we have seen it. And that optical rotation formula can be given as phi equals to 180 into length into L minus NR divided by wavelength. And therefore, with that, we can calculate the optical rotation. So this we have completed for the 4th week. Now, if you guys have any question or any doubts for that, whatever I have discussed or from the previous weeks, you can just unmute yourself or put your question across the chat box. I will be happy to answer it. Thank you. So it is just a gentle request that live sessions are starting from 7 to 9 p.m. So if you guys attend it at 7 p.m. sharp, so it would be helpful because in 1 hour I have discussed all the things. If you want me to repeat it, I can do it. Either unmute yourself or put it in the chat box so that I can repeat all of the things one more time. So I will just brief whosoever has joined now only. So these were the assignment problems for the week 4 lectures. And week 4 lecture was totally about the chirality and the light matter interaction. So the first question was the chirality is a key tool for biology because chirality, what we mean is something which is mirror images, but they are non-superimposable with each other, and they help in molecule recognition. So the three options were whether they help in molecule synthesis, no. helps in disintegration of the molecule? No. So the second thing is the molecule recognition is happening. Why we are saying that molecule recognition, as I have explained earlier, that if this is one molecule, and if we have these three shapes, so this is a kind of lock. You understand the lock and key mechanism. So this particular shape can only fit inside. If this is trying to fit in, they will not fit it. There will be some kind of void. So that means molecule recognizes whenever there is some other entity which is going to come inside. For example, this mechanism happens when we are making some antibacterial medicines or drugs or something like that, for that matter. So chirality plays a very important role. If we have a chiral center, that will recognize your molecule and it will play accordingly. And this is where the whole topic is around the chiral molecules. Now, the second question was, for a transition to be allowed, the value of the transient dipole moment should be. So transient dipole moment is nothing but we understand that light is comprised of electric field and magnetic field, which is the electromagnetic field we call it. Both electric field and magnetic field are perpendicular to each other. So when we have a light striking on, so say for example, this is my ground state, this pen is my ground state, and all the electrons would be staying here because having the less energy, the ground state would be mostly populated until unless the light strikes it. Now, when this light strikes it, it absorbs the light and it gets excited to it gets excited and goes to another level. Actually, it does not go to any level. It's just the perturbation of their orbitals. So why that light actually affects, what light actually does, and it makes it to go above. So this is what we firstly discussed here. So say for example, among the two, electric field and the magnetic field, electric field is having a major portion. Magnetic field is very low in amplitude, so it does not affect that much, but it does affect, but in a different aspect. So if we are taking this electric field, and this is my substance which is having an electron density, as soon as electric field interacts with it, there would be certain kind of perturbation. There would be a redistribution. Earlier it was in a circular motion, now it is having a different shape. So it is just for understanding purpose. So this electric field has actually perturbed its electron density, and we know from the Schrodinger wave equation that H psi equals to E psi. So whenever there is a change in your wave function, that will change your Hamiltonian, and correspondingly your energy will be changed. So earlier it was energy of the ground state. Now, since everything has been changed because of the perturbation, it goes to the excited state. So this is why photons, when light strikes your electron, it gets absorbed, and then therefore there is an excitation. So why we are particularly focusing on light and matter or something like that? This is because we need to understand that light, we are talking about the chiral. We are interested in chirality to have a molecular recognition. That is why we are focusing on the light. How is it interacting? Now, say for example, we have the light, we strike a light on a molecule, but how do we know what is the content of interaction is going to happen? So for the content basis, firstly, whether that transition, this is a ground state and this is an excited state, whether the transition is allowed or not, that depends upon this transient dipole moment. We know that dipole moment is related to the electric field, and dipole moment is given as electric field multiplied by its polarizability. Polarizability is nothing but the redistribution of your electron density. So this is a transient dipole moment, and it is given as ranging from minus infinity to infinity. The wave function at the excited level, the magnetic moment vector, the wave function at the ground state, and d tau. D tau is nothing but your volume element. That means in each direction, it would be dx, the element that is in dx, the x direction, dy, and dz. So when this whole value after the integration, if it is 1, that is the maximum value, that means it is allowed transition. So whatever the transition we are talking about from ground to excited, that would be allowed. And if this value is 0, that is called as forbidden transition. That can't be allowed. So this way, how we can define that whether the transition after striking of the photon on the electron state in the ground level, whether the transition is going to be allowed or forbidden, that will be accompanied from the transient dipole moment. So this is what we understood from the light and matter interaction. Now the second question arose that how much the substance, because electrons can't be like freely moving, it could be in a certain substance. So how much that substance can interact with the light? Say for example, I have this substance which is having electrons, and here I am striking the light. But how much it is going to interact with it? There would be certain factor. That factor is actually called as an absorbance. So this is my, say for example, solution where electrons are there, and here it has absorbed I naught value, and it is emitting. Some of the amount would be definitely emitting, not less. To have an energy conservation, we need to have certain amount getting absorbed and certain emitted. So the absorbance would be given as logarithm of I naught by I value. Therefore, it is a unitless value. These kind of small questions could be basic questions can be asked in the exam also. Now, we understood, okay, light is striking, some amount would be absorbed, some would be transmitted, and this is the value. But this absorbance is also dependent upon certain factors. So that depends upon concentration, that depends upon the path length, that also depends upon the epsilon value, which is the molecular property. For example, if I have two beakers, where one is having a concentrated solution, other is having a diluted solution, which one is expected to be having more absorbance? If you know the answer, it would be very good that if you can unmute yourself or put answer in the chat box. So if you have a concentrated solution, A is your concentrated one, B is your diluted one. Between two, which one is going to have more absorbance? Any answers? Hello? If at any point of time you are not understanding what I'm saying, you can just let me know so that I can explain it better. Can anyone answer? Like A will be having more absorbance or B will be having more absorbance? It is related to Beer's-Lambert law. So if you understand Beer's-Lambert law, you will be able to define it. Okay. So if there is more concentration, there would be more tendency of absorbing the light because it is interacting with the electrons. So more electrons, more concentration, more will be the absorbance. Similarly, if this is my distance that a light has to travel, and if this is the distance the light has to travel, so here absorbance will be more because the longer the distance it is traveling, it will be having more absorbance. And the third is the molar absorbance coefficient. That is the molecule's property. So what kind of transitions it is having, and therefore corresponding to that, epsilon value would be different. So this is what we understood now. Now the last point was that whether our light that I am talking about, which strikes on the matter, whether it is chiral or not, because the whole point of understanding on reading or delivering these lectures, it is just to understand whether the light that we are seeing, it is chiral or not. So generally what we have, the white light, right, this way our electromagnetic radiation works. So this would be a crust and trough. So if I'll just draw it in an arrow form, so it would be like this way, then it is like this, now this is point, this is down arrow, this is down arrow, and something like that. So if I draw like this way, it would be here. So correspondingly, it would be going like this direction. So the white light would be going in every direction. This is your white light. And when we are putting a polarizer in between that, it resects into one direction. That is called your polarized light. The polarizer will absorb all the direction, the light in all the direction, but excepting one, and that one would be the polarized light. So if my light is going like this direction, that right side, its mirror image, this is just one direction, would be like this way. Now these two mirror images are actually non-superimposable. Therefore, polarized light becomes scattered. So this is the whole crux that we found, that okay, white light can be converted to plain polarized light by using a polarizer. And once that either it is moving in the right side or it is moving as a left side, both are the mirror images and they are non-superimposable. Therefore, it is scattered. So if I have a molecule, and if this is my molecule, and if it is being placed in a polarized light, it will either rotate the light in right direction or it rotates the light in left direction. For example, if the speed of your right circularly polarized light is greater than LCP, say this way. So this is more towards the speed of your right circularly polarized light is more compared to the left one. So this is your left one. It is just going this more. So this amplitude or this magnitude is more compared to the LCP. So as a resultant, it would be having the direction as this way, right side. So this we called as optical rotation in right side. And this optical rotation is defined as, this is the formula where N, L, and NR are nothing but the refractive index, because refractive index is the ratio of your speed of light and speed of light in medium or something like that. And L is your path length and lambda is your wavelength. So based on that, we can actually calculate or quantify the phi of a certain compound in plane polarized light. So is there any question till now? If there is any question regarding the earlier lectures also, you can unmute yourself and ask me.
Recently I joined in this session, so I cannot ask any questions. Hereafter I will listen. Then, if I have any doubt, I will ask to you.
Okay, great. Actually, yesterday the slot was from 4 to 6, and I found that you joined after 6 p.m. Maybe you got confused with the timings. Last Saturday there was no live session, so that's why yesterday also there was a live session. I will upload the video, and it is a request to all of you that you please join right at 7 p.m. because after discussing all the things, then if you will join, you won't be able to understand properly, even if I'll try to explain it
That's
once.
fine.
Yeah.
Already I know the session will be start from 7 to 9, but I have one meeting at the time 7 to 7:40, 7:45.
Okay.
So I came later in this session.
That is not an issue, but yeah, because to make you better way understanding, it would be good for me also and convenient that if you are on time. So otherwise, you can go back and watch the videos at any point of time, and then if you have any doubt, you can ask me in the next live session also. So besides that, if in the live session first and second, if you have any other doubt, which we were talking about the symmetry and the point groups, that also if you have, you can ask me. So what I just told you, you understood about this chirality and light matter interaction, or is there any doubt? The absorbance that we talked about. So I can explain it one more time.
Ma'am, the molecular recognitions means here.
Sorry, molecular.
Molecular recognitions,
Yeah.
then one arrow, then chirality. Just simply, you will explain, ma'am, here.
Okay, so here I was actually talking about that why we are looking for a chirality. Earlier we saw that we were talking about symmetry and chirality, how the molecules are having that symmetry and whether they are being called as a chiral. So in last two live sessions, we were talking about the chiral point groups, if you remember. So for a molecule to be chiral in nature, it should not have a SN, that is improper axis of rotation. It should not be having any symmetry,
Improper.
right? So that matter,
Yes, ma'am. Yes.
it should belong to these polar point groups, that is CN or DN. Up to this point, you understood why we were saying that?
Yes, ma'am. Already I listened this session. I understood.
Okay. So once the chiral point group is there, now where are we going to use this chirality? Why are we even stressing on this chirality? Because if you will see that in our life system also, that biology, that RNA, DNA, proteins, carbohydrates, everything is chiral in nature. So to understand their properties and to recognize why do we actually talking about the chirality? Because if we have to synthesize a drug, which is going to affect a particular bacteria, so that molecule recognition actually requires the chirality. Say, for example, as I was showing that, say, this is my, say, for example, this is a bacterial wall or something. So here there is an empty space. And if I have a molecule which is chiral and which can stop its activity, it will go and bind with it and it will not allow it to again grow or something like that. It will stop its growth. So this is just a hypothetical situation that I'm telling you. So for that matter, the molecule recognizes which side it has to go, where it has to go. So that molecular recognition comes only when it is chiral. So to formulate a drug or to inhibit a bacteria growth or anything, chirality becomes a major tool in biological systems, and therefore we need a chiral systems, and therefore for chiral systems we need to understand the symmetry. We need to understand how the light and matter interacts and how we can quantify it. Now is it clear that why we are talking about the molecule recognition? Because our whole biological system is made up of a chiral molecule. Say, for example, RNA and DNA and proteins. Proteins are nothing but a chain, a polymeric chain of your amino acids. Now, what is amino acids? Amino acids are also chiral in nature that we studied in last lecture. If you'll go back and watch the video of amino acids, say, for example, we have 20 natural amino acids. So, general formula is this is carbon. The chiral center would be having all the substrates different that you know, right? So chiral would be having all the substrates different. So this is one R. R could be any group. This is any group. Based on that, we have naturally occurring 20 amino acids. There would be one H. There would be NH2 amine group because we are talking about amino acid, and there would be COH, the carboxylic acid. So this is alpha because at the same carbon we are having amine group, we are having the carboxylic acid group. Say, for example, if I am having this way. So now this is alpha because it is attached to the COH group, and this is beta. So this is no longer a alpha amino acid because your amine group is now at the beta position. So if I'll talk about this center, firstly, this carbon is chiral, and this is an amino acid. And depending upon what kind of R I'm taking, what R I'm choosing, it would be having different name, different things. And our proteins are made up of these amino acid streams. So when I'm talking about the proteins or carbohydrates or anything for that matter, it is involving chirality. And when chirality is there in every biological system, it helps us to recognize the molecule whenever we are targeting certain application, say for example, drug making or inhibiting the bacteria growth or allergy or something like that. So that is where the chirality plays a very important role. Now, up to this point, is it clear? Then I will move further.
Okay, ma'am. I am understood.
Oh, so now depending upon this R, we have 20 naturally occurring amino acids. So there are types like if R is your aliphatic group, they are called as aliphatic amino acids. Say for example, if I have H, NH2 and COH. So my question to you is, firstly, this amino acid is called as glycine. Is this chiral or not?
Chiral, ma'am.
Yeah. Why is it so?
Because two hydrogen atom is present. The four groups is different means that is chiral.
Right, you're absolutely correct. So these two are there. So this is only the exception where the glycine is such an amino acid which is not chiral. Whereas if I will take here carbon and now in this R was being substituted by H. Now in place of this H, I'm giving CH3. This is H, NH2, and this is your COH. This is called as alanine. So there are different names of amino acids, different symbol, which has been covered in the last live session. I would request you to go back and watch that. That would be easy. I have explained each and everything in details over there. Now, this is chiral or not? Alanine?
Alanine is chiral, ma'am.
Yeah. So now I will explain you. We have among the amino acids, we define it as L or D amino acids. So these are two types of isomers depending upon how they have been, how they are oriented. So general example, if I have R, where R could be anything, H, NH2, and COH. So this is general amino acid, alpha amino acid. Now we need to apply a rule which is called CORN rule, CORN, where CO stands for your carboxylic acid group, R stands for this R substituent, and N stands for your NH2. So whether my amino acid is left side oriented or right side oriented, or it is L form or D form, because you will come across L amino acids, D amino acids. So how do we assign that L and D form? By using this CORN rule. So what we have to do, wherever the COH is there, carboxylic acid, you name it as 1, R group as 2, and NH2 as 3, and then C. Whether going from 1 to 2 to 3, is it clockwise? Then it is D form. If it is anti-clockwise, then it is L form. Is that clear?
Okay, ma'am.
Okay. So now here this general form we have taken. Normally most of the amino acids which are naturally occurring, they are L amino acids. So here now I have this carboxylic acid. I will mark it as 1. I will mark my R as 2, amine as 3. Now you tell me if it is going like 1 to 2 to 3, 1, 2, 3 like this way, what direction it is? Is it clockwise or it is anti-clockwise?
Anti-clockwise direction,
Yeah.
ma'am. L configuration.
Right. So it will be an L amino acid. Whereas if we will change it to this form, if I've taken an example of alanine for that matter, and I am keeping my COH here. Now NH2 is here and H is here. Now if I'm assigning, depending on the CORN rule, if I'm giving this as 1, this as 2, because here the R is CH3 and this is 3. Now 1, 2, and 3, they are going to clockwise direction. Now this form will be called as D or L.
This is D configuration.
Yeah. So this is D amino acid. So these kind of questions can also be asked in your exam to find out the actual isomer form, whether it is L form, whether it is D form, which kind of rule you are going to apply. Based on that, you will be able to answer this question.
Ma'am.
Yes.
Ma'am, I have one doubt. First preference goes to COH. Second preference goes to CH3.
Right.
I think the second preference goes to NH2 group.
No, depending.
Because that is the.
We are not talking about your preference. See, I think you are confused with that Newman projection or something. For defining these L and D isomers in case of the amino acids, we have to follow the Kohn rule. I'm just going with that. I'm not going with this particular NH2 or something, CH3. I'm talking with this Kohn rule. So Kohn is firstly you have to give COOH as 1. R you have to give
Yes,
a
ma'am.
second reference. So R could be anything. It can be CH3, it can be
Oh.
CH2, CH3.
Okay, ma'am. Okay, now I can understand. I am confused with the Newman projection.
Yeah, so that is different. But to define, because that projection is for particular configuration, you are talking about some different isomers. But here, in case of amino acids, that 2 alpha amino acids, when you are talking about this L and D, depending on the rotation of your positions, and also the condition, your H has to be at the back position always. If it is not at the back position, you will not be getting the same result for the after applying the Kohn application. So this H has to be fixed at the back side. It should be back at the back side of your plane, and NH2 should be your above the plane. And then you have to assign carboxylic as 1. R group for anything. R group could be aliphatic, aromatic, polar group, or it is sulfur group, or anything for that matter, depending on which we have assigned the amino acids. And NH2 has to be the third one. Now then see rotation from 1 to 3, whether it is right or left. If it is right, then it is D amino acid. If it is left, then it is L amino acid. Is it now clear?
Clear, ma'am.
Okay. So, yeah. Once we know that, okay, these are the amino acids, and because this is very important, the next lectures would be regarding the circular dichroism, which is actually meant to know chirality of your DNA, RNA, all the biological systems. So that tool is very important to understand the biological systems. And at the last ones, I think in half of the weeks, we will be having mass spectroscopy. So that is a different concept. So here, what we started with the symmetry elements, operations, then we related with the mathematics, then we related the symmetry of the molecule with the chirality. Now chirality has been related with the biological systems, and then we had then we talked about how the perturbation could happen, how light interacts with your matter, how it when we say that okay, optical rotation is happening, it happens in a plane polarized light. What is the meaning of plane polarized light? How it is going to the right direction, how it bends your plane polarized in the left direction. It depends upon the chiral environment that you are giving. So in that case, amino acids understanding and their basic terminology, there would be a 3-letter code. There would be 1-letter code. So you need to actually understand what are these. For example, if I'm talking about the alanine, the structure that I've drawn over here. So its 3-letter code is ALA, whereas its 1-letter code is A. So these are very important. That comes under an aliphatic amino acid. So if you'll watch this one, that would be easy for you. But since you have joined late, so I will explain the questions one more time. So that would cover all your concepts. So here the first question, as you can see, it was simple that chirality is a key tool for biology because it helps in molecule recognition. As I told, that lock and key mechanism it follows. If it knows that this particular chiral molecule can only fit a particular position, that is site dependent. So chirality enhances the recognition. So it remembers like if this site, this much shape, this much space it is going to create, and therefore the chirality becomes very important. Then the second thing we saw that, okay, the transition has to happen from the ground state to the excited state. Whenever the transition happens, whether it is allowed or not, there would be many states that it can go to higher excited state, it can go to even more higher excited state, but which ones are allowed? And that is dependent upon this transient movement integral, where if the value is 1, that calculation also we will see in later point of time. If this is 1, and then it is allowed. If the value is 0, that is forbidden. So the question was straightforward, whether the value is 1 or not, then only it would be allowed. Third, I have already told you, when we were talking about the interaction of the light with the matter, how the matter would be knowing ki how much interaction it is going to happen. So, for example, I have given too much of light to my system, but there are very less amount of molecules, or it is a diluted version. It won't be able to interact with most of the light, and rest of the light would be emitted. So, for example, X amount of light has strike the molecule. Now, molecules are very less in number. They could absorb only little amount. Y amount has been left out. So Y would be greater than what it is actually absorbing. So absorbance then depends upon the concentration of your molecule. If your molecules are highly concentrated, that means it is going to absorb the light a lot. Then if the path length of traveling path length, like this is going from one point to other point, this is a long path, that means the absorbance would be more because it got the time, it got the distance to absorb the light. And also the third property of your molecule itself, like how much interaction it can do with the electric field. That field is coming and how much it is getting interacted, that is called the oscillating field, and that comes from the area under the curve between epsilon value and the wave number value. The next question was, since we know that molecules are generally having n to pi star transition, sigma to sigma, these are nothing but your orbitals which are involving and which are having the electron density. So pi to pi star transitions are very close to each other, and they, because of the same orbitals, same shapes, the transition becomes very allowed. So therefore, the epsilon value is very high for the pi to pi star transition compared to n to pi star transition, and then DD transition, it is having the minimum. Now the fifth question was like, what are the statements which are true for a plane polarized light? As we saw that when we are having a light from sun, that is white light and that goes in every direction, that can't be a plane polarized light because all the directions it is going, so it is not restricted to one thing. Now when we have put a polarizer which will absorb all the directions except the one, so it is giving only one light. One light means one frequency or one wave number, and that is called as a monochromatic light. That's why the first option is right. Whether the plane polarized light is chiral or not, that we saw, because if it is moving right side or if it is moving left side, the mirror images, the two things, the right motion or the left motion, they are non-superimposable mirror images. Therefore, they are called as chiral. So only first two options were correct. Then the sixth question was, if I have a molecule and now my plane polarized is coming. Now plane polarized light can be in both directions, right side also, left side also, because it goes like a electromagnetic radiation. Now if the right side thing, or the, here it is written that it is mostly towards the left side. So if it is most towards the left side and the right side arrow is very less, so the resultant of the two would be in the left side. So the molecule which is chiral, that will affect your plane polarized light and make it to rotate in the left direction. So that is what the optical rotation term comes into picture. And the last question was regarding the optical rotation value only. There is a formula of phi is equals to 180 into L, which is a path length, NL minus NR, which is the difference between the refractive index of your LCP and the RCP divided by wavelength. So divided by wavelength. So we don't need to actually find out anything. If you will clearly see over here, I have given NL is equals to NR. That means refractive index or the speed of light in that medium. It is NL equals to, refractive index is same for both the LCP and RCP. That means not if both the things are equal. Say for example, if it moves to this direction, right LCP, and this is left. So resultant would be nothing. It would be at the center only. There is nothing to happen. Like it is not going to rotate your molecule in either direction, because the first half in the right direction, the second half has cancelled the rotation from each direction. So therefore optical rotation becomes zero. So there phi will be zero. So is that clear? I understand it would be a bit faster, but since we are short of time, maybe you can go back and rewatch these videos and also the videos that have been uploaded by Professor. Then it would be more clear to you. And if still there would be any doubt, you can ask me in next live session. So still, if you have any question, you can ask me.
Okay, ma'am, no doubt.
So can you see this video,
Okay, ma'am, I see.
right? So see how it is moving. So this is your light only in a one direction, but how the oscillations are happening. So this site, I will just put this link in that PDF or the presentation, which I'll be sharing the folder. So here you can see and understand the plane polarized light in the absorbing medium, how it works. Like first it going up and down, up and down. So this way we can see that. Also, so here, this is the vector of the electric field. How is it going? So this is the 3D view, how the crust in front it goes. And the front view, if you will see, you will only be seeing as an up arrow and the down arrow. That is where we do it. So these are the circularly polarized waves that I was talking about now, whether it goes to the right side or it goes to the left side. So as you can see, this is going in a right direction. You can see it. So this side is very useful to understand the circularly polarized light, how it transfers in a light absorbing medium, and how do you see the right circular polarized light or the left circular polarized light. So this side, I will just put it in the here.